So let's take a look at dependent motion. This is motion of one object directly related to the motion of another, often because they're somehow connected with a rope or a cable or some other sorts of device. So some of these problems are pretty basic. This one, for example, has a single pulley with two blocks. So obviously if block B goes down, block A is going to be going up. Alright? Some of these are more complicated. So this one has 3 pulleys in one block, but the one block is attached in 2 different places to the pulleys. So if I pull down at B, block A is going to go up, but not necessarily at the 1.5 meters per second that's shown. This one's even more complicated. 3 pulleys, two objects, but there's 2 ropes, right? So one rope attached starts at F, goes around pulley D, around pulley C, and attaches to block A. The second rope starts at the top at pulley C, goes around pulley E, and attaches to pulley D and block B. So as A goes down, block B is going to go up, but once again not at the 4 feet per second. Another option is where you have angles involved in your system, right? So the truck is moving outwards, the case is moving upwards, and the velocities of the two, the motions of the two, are related somehow through the trigonometry of this triangle. So, a general approach to these types of problems is to identify something in the problem that is constant. Usually, the rope length is constant, right? So, the rope isn't going to change length. Each segment of the rope might change length, but the total length of the rope isn't going to change. Then using that, we can solve these problems. So the first thing we need to do then is to establish a coordinate, an origin, that's at a fixed point, and then for each object that we're interested in, we're going to, or each segment of the rope, we're going to draw from a fixed point to that object along its path of motion, and that's going to be our distances. Next, we're going to use geometry or trigonometry to relate all the position coordinates to the total length of the rope. While we're doing this, we can ignore sections that don't change length. And we'll see this in the examples. We repeat this for all of the different ropes or cords in the problem. Then we take time derivatives or differential elements to find either the velocity of the acceleration in terms of time derivatives or a change in position for the differential elements. And then we look at our signs, and we can tell from our problem if one box moves down, the other box is going to move up or down or something of this sort. We need to make sure that the signs in our final answer match that. So let's take a look at a basic example here. Here we have 3 pulleys, 1 rope, right? So the goal is to write the length of the rope in terms of the lengths of the segments. So, first thing on our list here was to establish a position coordinate for each object with a fixed point location. So if we pick this line up here as the datum, you can see that that's fixed, right? These pulleys don't move, they're attached to the roof or the ceiling. So that is our fixed point. So point B is some distance, I'm going to call it SB, down from that fixed point. Then we have these 2 segments are the same length, right? This one and this one. I'm going to call this distance then SA. Then, if we take this over here, right, we can also call this SA, right? Same distance down. This section, let me make my pen red. There's some sections of this rope that aren't going to change length. right? So this section here that moves over the pulley is not going to change length. This section here that moves over the pulley is not going to change length. This section here on the bottom side of this pulley is not going to change length, and this section down here is not going to change length. So we're going to ignore those, because when we take the derivative of something that doesn't change length, it goes to 0. So then we're done with defining all of our lengths. So if we write the length of the rope, we've got SB, right, plus 3 times SA. There's this part, that's SA, that's SA, that's SA. And then the rest of it are the red parts that don't change length. So this is our length of the rope. Now, if we wanted to, so I'm going to add some things to this problem just so we can see some examples here. If I was told that I moved point B down, so if SB changed, so delta SB equals, I don't know, how about 0.5 meters? So the guy who grabs it moves his hand down 0.5 meters. How do we figure out how far up SA is going to go? Well, we can do that with differential elements, right? So the length of the rope isn't going to change. So delta L is going to equal 0. Is equal to delta SB plus 3 delta SA. Right? The change in SB plus 3 times the change in SA has to equal 0. So delta SB is equal to 3 times delta SA, negative. And so delta SA is going to equal 0.5 divided by 3 meters. And SB was down and SA is up as our directions. So that's how we would do things with differential elements. Now let's do things with finding the speed. Alright, so with finding the speeds, we're going to take the derivatives. So L dot is equal to SB dot plus 3SA dot. The derivative of the length, which doesn't change, is 0. The derivative of distance SB is VB plus 3VA. Well, we're given VB is 1.5. So 1.5 is equal to negative 3VA, or VA is equal to 0.5 meters per second. So this is then the speed of VA. The direction, VB was down, VA is up. So notice instead of writing this sign, I drew the direction. It's upwards. Alright, let's look at a slightly more complicated example. Here we have an elevator. So there are motors up at the top of the elevator that are wrapping the rope up around themselves, right? So that's how the motor is working. So instead of thinking of it as a motor wrapping up the rope, because that gets confusing because technically the rope is then getting shorter, we're going to replace in our minds, just imagine replacing those motors with a giant hand, and that giant comes in and grabs the elevator cable and pulls upwards. Alright? And the giant is pulling with a constant speed of 5 meters per second. And the question is, how fast is the elevator moving? Alright, so if we look at this picture, we've got 2 ropes. Right, one rope goes from B, let's give these things some letters. Alright, let's call this pulley down here A, B, C, D, E, and F. Alright, so one rope goes B, A, D, E, right? And the other rope goes from the elevator up to E, down to F, up to C. Alright, so we need a fixed point. I would recommend using here the center of this pulley D as our fixed point. Alright, so then from the center of the fixed point, from that fixed point, up to B, right, where the giant is holding onto our rope, would be SB. All right. From that fixed point down to A would be SA. Then we've got, on the other side, we've got from the fixed point up to the giant at pulley motor C would be SC. From the fixed point down to the pulley on the elevator would be SF. And we also have this pulley E that we need, so we need to go down from the fixed point to pulley E, so that's SE. Alright, so now we get to write our length of the rope in terms of these variables that we just wrote. Something to notice, first of all, SB and SC are going to be the same, right? Because the elevator isn't going to tilt. So those two are going to be the same, and then SA and SF are the same. So let's just jot that down so we remember. SB is going to equal SC. SA is going to equal SF. Alright, so let's write these lengths. Length 1, that's the one that starts over here. So we've got SB, right? That's the first part. SB plus from here down to the pulley would be SA. Plus, then we go from the pulley back up to here, so that's SA again. Plus, from here down to there would be SE. Alright, that's L1. L2 is the other rope, so it starts down, well, let's start up here. We've got SC plus SF, right, all the way down to the elevator. And then it goes up from F to E. So that would be this distance, right, which is SF minus SE. All right, so plus SF minus SE. All right, so let's rewrite, we'll combine some things here, rewrite this. So we've got 2SA plus SB plus SE. Here we have SC, which is the same as SB, SF, which is the same as SA. So we've got 2 SFs, so 2 SAs, plus SC, which was the same as SB, minus SE. Is that right? Nope, there's one more SE, right? So we have SC, SF, SF minus FE, and then another one of those same lengths. So there should be a 2 here. So then that would be, let's see here. So then we have 3 SFs, so 3 SF minus 2 SE plus SC, which was same as SB. So now if we look at our numbers or variables, SF is the same as SA. All right. So we've got SA, SB, and SE, 3 variables. So we're going to combine these 2 equations to get us to one equation with 2 variables. The 2 variables we want are going to be SB and SA, right? Because we want to relate the given velocity of B and C to the velocity of the elevator, which would be A. Alright, so let's take the derivatives. We've got L1 dot equals 0 equals 2 SA dot plus SB dot plus SE. And L2 dot is equal to 0 equals 3 SA dot minus 2 SE dot plus SB dot. Alright, let's solve this first one for SE, because that's the variable we don't care about. SE dot. And we can rewrite this, let's rewrite these as velocities. So VA plus VB plus VE. And this is 3VA minus 2VE plus VB. Alright, so this first one can be rewritten for VE as VE equal to negative 2VA minus VB. And that can be plugged in here then, right? And we get 0 is equal to 3VA minus 2 times negative 2VA minus VB plus VB. Yep. Okay, so let's write these out. 3VA minus plus 4VA minus 2 minus VB, so plus 2VB plus VB gives us 7VA. Oops. VA plus 3VB. So we are given this 5 meters per second is equal to VB. So VA is equal to 3/7 of VB, which is 3/7 of 5, which is 2.14. The direction, well, the units are meters per second, and the direction is upwards, right? Because the motors pull up, the elevator goes up. All right, so our answer is 2.4 meters per second. Our last example here is one of these ones with angles. So what happens here is the father has his son on the rope, right? So initially it says that when XA is 0, so the dad is right by the boy, YB is 8. Okay, so there's the 8 when the dad's right up against him. That means that the total rope is 16 meters long. Okay? So L is 16 total. Then he starts walking backwards, right? So he's going this direction with an acceleration of 0.2. And he walks a distance XA, and in walking the distance XA, the boy goes up until YB, right? It's until YB is 4. That's the point we're interested in. Alright, so if YB is 4, can we figure out what the speed of the man is at that time? Alright, because we have to do speed and acceleration. We're asked, actually no, we're just constant acceleration, determine the speed of the boy. We're looking for VB. That's our ultimate goal. Okay. So chances are we're going to need to relate VB to VA, right? Because that's what we do, is we relate the velocities of the two items on our list. So we need to find VA as well. So how do we find VA? Think back several lessons, right? We've got a constant acceleration, so we can use one of our constant acceleration equations. If we look at those equations, the one we want to use is VA squared minus the initial velocity squared. Initially he was standing still, so that's 0, is equal to 2 times the acceleration of A times XA minus the initial position in X, which is also going to be 0 because he's right up against the boy at that point. Alright, we know the acceleration of A is 0.2, so VA is the square root of 2 times 0.2 XA. Alright, what about XA? What's XA? Well, if we look at, this is a triangle, right? One leg is 8, the other leg is XA, and let's call this side S. Right? So we know that S squared is equal to XA squared plus 8 squared. And we also know that the total length of the rope, right, is S plus YB, right? And we're told YB is 4, right here. So if YB is 4, then we've got, this is equal to 16 is equal to S plus 4. So S must equal 12. Plug that in up here, right? We get that XA is equal to 8.94. Plug that in up here, we get that VA is equal to 1.89. All right, so now we're at the point where we started the last problem, right? We're given the velocity of the man. We need to find the velocity of the boy. All right, so now we need to relate the motion of the man to the motion of the boy, and it's not as simple as with the pulleys because we have this angle involved. All right, so let's take a look then at our definition of the length of the rope. That's where we started before. We've already written it, right? The length of the rope has 2 parts. It's S plus YB. Okay? So if we take the derivatives, we get L dot, which is equal to 0, is equal to S dot plus YB dot. YB dot is what we're looking for. That's our velocity. Question is, what is S dot? Well, we've already written an expression for S, right? So S squared is equal to XA squared plus 8 squared. Okay? Take the derivative of both sides because we're trying to find S dot, right? So 2S S dot is equal to 2XA XA dot, and the derivative of a constant is 0. Okay, so then we have, do we know S? So this is general. Now we have this specific situation over here, right, where YB is 4, VB is what we're looking for, VA is 1.89. So we can write here S dot is equal to XA dot, which is VA, which is what we're trying to find, over S. All right, so let's take this over into this equation. We get 0 is equal to XA VA over S plus VB. We know VA because we found it over here. VB is what we're looking for. And we know S because we found it over here. And we know XA because we found it over here. So we should be able to solve then. So we've got VB is equal to negative 8.94, that's XA, times VA, 1.89, divided by S, which is 12. All of those things we found already. So we plug that in, we get VB is equal to, I'm going to leave the sign off, 1.4, and the man is walking backwards, the boy is going up. So the man's walking backwards meters per second, and the boy is going up, also in meters per second.